I teach in the systems engineering department. My educational background is heavily into systems engineering. A lot of my students and my audience on LinkedIn are systems engineers. That said, over the past few years, I've really become more interested in systems thinking, and I see systems thinking as being distinct from systems engineering, which I'll talk about a bit in this lecture and I talk about in other places. My teaching, my writing, my speaking are heavily influenced by systems thinking, and I find myself repeating themes from lecture to lecture. I thought I would tie them into this one lecture so that you don't end up having to watch the same slides over and over again as I try to use the archetypes I'm going to talk about here as part of deeper points. I leverage two great books on the topic. One is The Fifth Discipline by Peter Senge, and the other is Thinking in Systems by Donella Meadows. And you can see the books on the screen here. The two authors knew each other and each referred to the other in their own writings. That said, I spend a little more time with the Senge stuff on The Fifth Discipline. The Meadows book is very good. It's just Senge's stuff is a little closer to what I want to teach. The base concept is that systems follow feedback loops, and these are either reinforcing or balancing. In a reinforcing loop, growth encourages more growth. The traditional symbol is an avalanche in which a small disturbance at the top is continually reinforced until it wipes out all the ski chalets at the bottom of the mountain. A viral pandemic also follows a reinforcing loop, and I'll talk about that a bit here. In a balancing feedback loop, growth discourages growth. An example is a home thermostat. Once the heat gets too high, the thermostat will shut off the furnace and allow the temperature to drop, keeping temperatures close to some balance point. Note then that my minimal definition of systems thinking includes feedback loops. These are not addressed in traditional systems engineering approaches, which are based on decomposition. I also have other lectures discussing the differences between systems engineering and systems thinking. The COVID-19 pandemic was, of course, tragic and society-changing, but it also provides a foundation for deeper learning into systems thinking. For example, here are the daily confirmed cases of COVID-19 in the first 3 months after it was recognized by the World Health Organization. Graphs like this show up wherever there is reinforcing growth and are known as hockey stick graphs because they roughly follow the shape of a hockey stick. And oh, by the way, this is when I contracted what I'm sure was COVID. I sat next to someone with symptoms on January 10th, 2020, had my own symptoms on January 12th. My point being is that in a world of international travel, diseases can move around very quickly. I was infected just a few days after the disease was first recognized by the World Health Organization. If we look at the first 18 months of COVID-19, we can see recurring hockey sticks. In these cases, we can see a traditional flat slope followed by a rise. And in this period, we can see a decline followed by a rise, but again, it's the hockey stick shape. And in this period, we can see an inverted hockey stick. In fact, it's a pretty significant decline. Reinforcing growth could be either positive or negative. And I'll come back to this in a bit, but in the systems thinking nomenclature, reinforcing growth is drawn as a plus sign, while the inverted hockey stick or a reinforcing decline is drawn as a minus. It's interesting to look at this graph as a time lapse. In particular, that last spike there is at Omicron, and you watch this graph play out, and you keep thinking that you've reached the top of a mountain, and then you realize you just need to keep going back up to the top of another mountain. And even when you drop down into a valley, there's yet another mountain in front of you. Such is reinforcing growth. If we compare COVID cases to hospital admissions, on the left is a peak in the fall and winter of 2020, about a year after COVID began, and on the right is the Omicron surge, which happened a year later. But even though Omicron created 3.5 times as many cases, it only created 60% more hospital admissions. So while many more people contracted over Omicron, The percentage decrease in the number of admissions implies the beginnings of a balancing loop. Across those 40 months, we see periods of both reinforcing growth and decline. While Omicron was highly infectious, infected people were able to quickly fight it off due to vaccines, previous infections, and changes in social norms. In short, the virus was so successful that it eventually caused its own collapse. And from March of 22 to May of 23, we began to see a balancing decline as case counts were rising and falling in diminishing waves. Growth is becoming more and more difficult for the virus. This is a systems model which describes how reinforcing and balancing loops can occur with infectious diseases. It is known as an SIR model, in which susceptible people become infected and then hopefully recover. You can see that it is impacted by the number of infected people, the duration of contagion, and the opportunities available for infected people to meet susceptible people, as well as some likelihood that an infected person will transmit the virus and the likelihood that the person receiving the virus is susceptible. These factors are then impacted by things like PPE, masks, and social distancing. The graph results in a reproducibility rate, which is the number of people infected by each infected person. If larger or smaller than 1, then the virus will grow or decline exponentially. But if R0 is close to 0, or as we saw earlier where it's kind of going up and down a little bit, the disease will reach a balancing loop. Vaccines and surviving past infection leads to herd immunity, but the length of the individual's immunity is impacted by both reproducibility and mutation rates. And as we saw with variants, both the duration and size of the infected population leads to new variants, and the cycle begins all over again, albeit with some different level of herd immunity. And systems thinkers have a modeling nomenclature. This loop shows positive reinforcement. As susceptible people become infected, there are more infected people who put susceptible people at risk. This is when you see the upward curve on a hockey stick graph. But as the vaccinated and/or infected population recover, they become less susceptible to new infection. At this point, depending on the strength of the negative response, the virus will enter either a balancing loop or a reinforcing decline. In all, this is known as a limits to growth model, where an entity's growth reinforces itself until it either runs into an obstacle it can't overcome or simply runs out of resources. In the case of COVID-19, the obstacles were masking and social distancing, while the combination of vaccines and past infections reduced the availability of potential resources. So let's talk about limits to growth. At some point in the Middle Ages, farming communities organized so that one family devoted their attention to plowing the community's fields, and towns grew thanks to greater food security. By the 20th century, oxen were replaced by tractors. More food could be harvested by fewer people and transported further distances. The agricultural economy shifted to an industrial economy, and this phase is known as the Second Industrial Revolution. But this reinforcement is reaching its own limits, meaning that human growth is being balanced by nature. The space available for automobiles has become limited, and carbon emissions impact the climate. The global supply chain has grown such that human populations are growing into viral reservoirs, and a warming atmosphere is allowing dormant viruses to re-enter the population. The reinforcing growth of people and prosperity are triggering counteracting forces from the planet. We can also track this growth in the concentrations of atmospheric carbon dioxide. When our ancestors first arrived 300,000 years ago, atmospheric carbon was about 280 parts per million. At the end of World War II, it had increased to 312 parts per million, and a generation later was at 320, an increase of 8 during that 20-year period. 20 years after that, carbon increased by 25 to reach 345 parts per million. Today it is at roughly 420, an increase of 75 parts per million over the past 40 years. And on this graph, 560 parts per million will be about here, which is about the same increase as from 1945 to today. But note that the pace of change is increasing. 560 is interesting because the last time this occurred, the planet was so warm that alligators could live in the Arctic. With this in mind, I feel like we're approaching a limit to growth, at least in terms of the human species. We may also be reaching a limit to growth in the viability of the auto industry. This picture is from somewhere around 1930, and you can see the creation of an early highway without a lot of traffic. In the 1950s, Congress passed and President Eisenhower signed the Federal Highway Act, which provided a great deal of federal funding for highways throughout the U.S. These two actions created a reinforcing growth. And first, the highways got longer, meaning that it was possible to drive a car from, say, New York to Los Angeles. And as cars became even more popular, the highways were built wider and wider. But seemingly no matter how wide we make our highways, the number of vehicles grows until all available space is consumed. This is a classic limit to growth model. So the talk of the past decade or so has been to automate driving, to make vehicles, at least in theory, safer, highway traffic more efficient, and allow passengers to sleep, read, or watch a movie while the car drives itself. But safer, efficient ground transportation, which allows passengers to do other things while commuting, has been available for centuries. People who know me or take my class know that I am a big fan of trains and other sorts of mass transit. And as I discuss in other places, quantities of batteries, magnets, and integrated circuits are also limited. We should expect that access to mobile power will be a problem, and transportation devices like trains and trolleys, whose power supplies remain permanently connected to the ground, will be the future of transportation. Or for that matter, Zoom or Teams or FaceTime and any of the other online collaboration apps. Something I find interesting is that students in what used to be an in-person class now prefer to take the course online, even when I hypothetically offer to send an autonomous vehicle to bring them onto campus. Many of these students work in the auto industry, and yet they prefer Zoom to driving, which in the long run disrupts their own careers. I'll get into this disruption in another lecture. Let's move on to another archetype called shifting the burden. In it, you can see that there is some problematic symptom and two possible solutions. One addresses the obvious symptoms with lower cost, immediate payback, and seemingly positive results. A fundamental solution may exist, but it is difficult to address because it is costly and time-consuming, and the symptomatic solution seems to work so well. But eventually a side effect to the symptomatic solution will appear. This will lead to a systemic collapse, and the collapse itself is reinforcing. As one element collapses, two which depend on it also collapse, followed by 4 and by 8, etc. You can make a case regarding burden shift with respect to world trade. From 1900 to 2008, globalization followed the hockey stick chart mentioned previously. Though from the 2008 recession to the end of this chart in 2014, you can see that the reinforcing growth moved into a balancing cycle, and even this was prior to the COVID pandemic. And beginning in 2021, a year after the onset of COVID-19, we saw a collapse in the global supply chains. World trade has been overwhelmingly positive for the growth of society, reductions in poverty, and increases in standards of living, going well back before the late 90s when this chart begins. And in the post-World War II era, world trade certainly seemed like a fundamental solution, and in many ways it was. But you can see a perturbation in supply chain pressure during the Great Recession from roughly 2008 to 2012. And there was a much more pressure during the COVID-19 pandemic, where supply chains collapsed. As I record this in December 2023, 4 years after the start of the pandemic, supply chain pressure has eased, but note that the size of the perturbations are increasing. I posit in other places that a more fundamental solution is to reshore supply chains. I envision a world in which global trade takes place in virtual products which are then manufactured locally, rather than trading in physical products to be shipped globally. Another terrific book, published in 2014, is The Butterfly Defect by Ian Golden and Mike Maria Faison. The traditional definition of risk assumes that it is quantifiable, calculable, and uncorrelated. The insurance industry has been very confident in this realm. They can calculate the risk of a single house burning or an individual being robbed and offer a payout if this happens to you. But the side effects found in a shifting burden create an uncertainty due to threats which are not in our models and seem outside the boundaries of the calculable solution. For example, if thousands of houses burn due to wildfires or flood due to rising sea levels, these events become uninsurable. The outcome of a systemic collapse is some new objective reality. The trigger to a systemic risk is known as a tipping point, and I discuss this in other lectures. In all, this leads me to question whether our current incentive structures continue to bring societal value. World trade has been a huge boon to the growth of humanity. However, it also accelerates the transmission of communicable disease, and in the course of that disease, supply chains may collapse. In creating global systems with seemingly positive results, we come to rely on systems with fundamental flaws, thus creating a systemic risk. The past few decades have brought massive societal value by shifting the burden onto low-cost manufacturing economies and helping the undeveloped world to develop. But this creates a systemic side effect that the global value chain lacks resiliency, as can be seen in these headlines. Finally, if delays exist in the system, it can be very difficult to recognize the impact of a change. The action taken may eventually have a positive impact, but due to the delay, it is difficult to tell. In mechanical and electrical systems, this is known as hysteresis or latency. In human systems, people unfortunately tend to get frustrated and they give up. I cover the impact of delays in more depth in this lecture video on a beer distribution supply chain, and we run that just supply chain simulation in class. For the last archetype, let me finish up with a tragedy of the commons. In it, multiple entities see reinforcing growth from only their own activities without realizing that they are depleting a common resource. You can imagine Farmer Allen and Farmer Betty each raising their own cow. They sell the milk from their cows and use the money to purchase more cows. However, the cows are grazing from a common field. As Allen and Betty's farms grow, their cows eat all the grass. The field, the herds, and the farming community eventually collapse. Allen and Betty's individual activities increase the combined total activity, and the total eventually reaches the resource limit, in this case, the amount of grazing land. A strained supply chain is also a tragic commons. As inventories were strained in 2021, many companies tried to increase their available inventories, but there were a finite number of ports, ships, trains, and warehouses, and the systemic effect was to increase the burden on an already challenged supply chain. And of course, there's only one atmosphere, and we are quickly reaching the limits of its ability to sustainably maintain the carbon we are putting into it. Each aircraft, each automobile, each power plant, etc., is very efficient at accomplishing its own goals, but the atmosphere is a finite resource, and the impacts are felt far away and long after the decisions are made. Capitalism, as defined by Adam Smith, is the aggregation of private property markets and firms. Corporations deliver products into the market so that they can be purchased as private goods by consumers, and this strongly incentivizes individual actions and creates a great deal of local economic success. But externalities are the impacts felt by others who are not involved in the market contract between buyer and seller. This can also be considered a burden shift. You can think of externalities as entities within the system which are not recognized by models of that system. The entities exist, we just don't account for them. Emissions created years ago created the conditions which in 2023 created a flood in Vermont, a drought in Nebraska, and a fire in Maui. Imagine if we monetize the cost of emissions. Imagine if the price of gasoline include the external costs of fire, flood, drought, and disease. But if everyone in just one region or even a country changes their ways, it will have no impact unless everyone else also changes their ways. In a tragic commons, there is no point in anyone to do anything unless everyone does everything. So let me wrap up. I see systems thinking as something quite different from systems engineering, most notably that systems thinking has feedback loops, which are either reinforcing or balancing, and we can see examples of this in pandemic diseases such as COVID-19. There are many archetypes, and I covered 3 here that I find important: limits to growth, shifting the burden, and tragedy of the commons. Look for matters in which systems can feed back upon themselves, and if your system model is not addressing reinforcing and balancing feedback, and if it is not addressing culture and economics, you are probably missing something. Finally, and I discussed this in other places, the cultural and economic systems we have been following for the past century are reaching their limits. We have created a systemic risk which will need to be accounted for very soon. Thank you very much for listening. Much of my course content can be found on my website at patrickhilbury.com. These posts are resources that I make available to you as students in preparing for the end semester debates, and I also use in my speaking and writing. Thank you.